In this lecture, we will complete our discussion on displacement thickness of boundary layer, and then subsequently we will discuss a bit on laminar and turbulent flow. So, in the previous lecture, we had looked at a diagram here of a typical velocity profile within the boundary layer, and we discussed about the velocity deficit that is noticed within the boundary layer. And then we further discussed that displacement thickness is essentially the distance by which external potential flow, that is the outer flow, would be displaced outwards as a consequence of the decrease in velocity, that is this, which occurs within the boundary layer. And as a consequence, the streamlines are also deflected because of this effect. Now, if you were to draw a velocity profile like this, which is inviscid in nature, I have purposely left a gap over here where no velocity is shown. So, all along in the rest portion the u infinity is shown, but you have a certain thickness next to the wall where the u infinity has vanished. Now, what is the implication of this gap? So, if we say that the distance the surface has to move in the wall normal direction, that means the y direction, to reduce the flow volume by an amount caused due to the velocity deficit in the boundary layer, then this is the distance by which the flow moves. This is precisely shown through this figure, where the rest of the flow is an inviscid flow, that is, it is devoid of the viscous effects, and therefore, it does not suffer from velocity deficit. So, it has no velocity deficit, but it is carrying the same flow as this viscous flow, and if it does so, then it has to displace from the wall by a distance delta dash or delta star, sorry. So, how can we mathematically write it down? We can write it down like this. We are integrating the velocity deficit over the thickness of the boundary layer, and we are taking unit depth. What will this give us? It will give us product of a velocity in the sense of a deficit and area, because it is the height times the depth, unit depth. So, product of the velocity and the area essentially will give us, in terms of dimensions, it is meter cube per second. So, it is volumetric flow rate, and this is the deficit that has been caused because of the presence of viscous effect, and we are balancing it with u infinity times delta star times 1. That is precisely signified in this diagram. So, if that is the case, then delta star can be represented as 0 to delta 1 minus u by u infinity t y. This will give you the displacement thickness. And as we already discussed, that as a consequence of this displacement effect to the potential flow, the flat plate looks slightly inflated. By what extent? By delta star. And consequently, the streamlines also follow that deflected shape or inflated shape, which is by virtue of the presence of this delta star. That means, the effective body shape looks inflated. If you perform calculations, you will find that delta star is a fraction of the delta. So, this was a brief discussion on the displacement thickness. Like we see a deficit in velocity within the boundary layer, and consequently we have a displacement thickness. Similarly, we will see deficit of momentum as a consequence of velocity deficit, and therefore, there is also a momentum thickness which can be defined. We are not deriving it here, but I leave it as a homework for you to explore that. So, with this we complete our discussion on boundary layer. Next we move on to a very basic discussion of characteristics of laminar and turbulent flow. As you know that in aerodynamics we can have different kinds of aerodynamic configurations which operate over a wide range of velocities, and therefore, you can have a wide range of Reynolds numbers. And some of those flows could be completely laminar flows, or some of them could be a mix of laminar and turbulent flow with a transitional part embedded between the two. So, we will have a brief discussion about the two regimes of flow and try to understand their differences in terms of the basic characteristics. Now, Reynolds number, as we may recall, is a measure of the relative importance of inertia forces and viscous forces. Now, if you perform experiments on fluid systems, it is observed that at values below a critical Reynolds number, Re critical, the flow is usually smooth. What does that mean? It means that adjacent layers of fluid slide past each other in an orderly fashion. That means, if you are looking at the streamlines, for example, they will be very orderly and they will most often remain independent of time. That means, the flow is by and large steady. So, if the applied boundary conditions do not change with time, the flow will remain steady, and this regime of orderly flow is called as the laminar flow. Typically, it occurs at comparatively lower values of Reynolds number. Of course, we have not yet defined what this critical Reynolds number is all about. At values of the Reynolds number above Re critical, a complicated series of events take place which eventually lead to a radical change of the flow character. In the final state, the flow behavior is random, chaotic and unsteady. The velocity and all other flow properties display this random behavior. This regime of flow is called as turbulent flow. Now, typically if you revisit the flow past a flat plate and formation of boundary layer, you may recall that the theories that we discussed were catering to the laminar regime of an incompressible boundary layer. So, if we continue with the incompressible assumption for now, that means for comparatively lower velocities, we start off with the same laminar boundary layer, but if we follow it for a considerable length along the streamwise direction, then what we will notice is that gradually some flow instability start growing within this boundary layer, and they also get amplified as we move further downstream. Now, as they get amplified, more instabilities develop and gradually it turns into a very different flow regime, which is the turbulent regime. Now, these changes occurring due to instabilities, onset of instabilities actually occur over a certain finite length. It is not that it suddenly happens at one location, but once that is crossed, you have a completely turbulent flow. And if you notice the boundary layer patterns starting from the laminar regime to the turbulent regime, you will find one very significant difference between the two, that is the gradient of the velocity within a laminar boundary layer is much shallower compared to what it is in a turbulent flow. That means, if you look closely to the near wall region, then you will find that del u del y for the laminar flow is significantly smaller than that of the turbulent flow. This is what we mean by a fuller velocity profile for the turbulent flow. And we will discuss later that much of this is due to the random chaotic nature of turbulent flow itself, that it attains this fuller velocity profile. And as we discussed that there were instabilities developed in this in between region, which we defined as transition. So, this part was laminar, the next one was transition, and the subsequent portion and further downstream is the turbulent regime. Now, apart from flow past flat plate, you could see laminar as well as turbulent flows in a lot of other types of canonical flows, like say 2-dimensional jets. Again, jets can vary in terms of their features depending on the orifice shape, and then you can have wakes formed behind bodies, like we discussed about wakes forming behind say a bluff body or an airfoil pitched at a large angle of attack. Then internal flows through pipes, and of course, flat plate boundary layer, which we already discussed to some extent. And there could be more flows which are more complicated than the ones we are mentioning over here. And in these different kinds of flows, the RE critical, that means where the changeover starts happening between laminar and turbulent flow, can occur at different Reynolds numbers. Typically, in a turbulent flow field, because you have a fluctuating component of the property that you are looking at, we try to express the property, let us say velocity, in the form of a sum of a steady mean component, mean in the sense time mean, that means you average the velocity over a finite time period and then extract this mean value. What is left is the fluctuating component expressed with a dash, and that is a function of time. Typically, if you are looking at a turbulent velocity field by inserting a probe into the field and trying to measure it, then this is how it may look like. So, once you acquire this data for a considerable time period, this is your time window over which you acquire it, you average it, then what you come up with is this capital V, often expressed with an overbar. And the difference between that mean and the fluctuating part at any particular time instant will be expressed by the difference, and that is essentially the V dash, which is obviously going to be a function of time. So, this is what is called as the Reynolds decomposition of turbulence. A turbulent flow can be characterized in terms of the mean values of the flow properties, which could be different velocity components, pressure, density, temperature, etc., and the fluctuations, which is u dash, v dash, w dash, p dash, etc., but in terms of some statistical properties. That means, if we keep recording these fluctuations even over large periods of time, we would not be able to extract enough pertinent useful information from these fluctuations. So, we have to extract certain statistical values. Even in flows where the mean velocities, that means this component, and pressures vary in only one or two space dimensions, turbulent fluctuations always have a 3-dimensional spatial character. That means, irrespective of the spatial variation of the time mean component, the time dependent component, that is the fluctuating component, is always 3-dimensional in nature. That means, it is going to be a function of x, y, z as well as time. Visualization of turbulent flow reveals rotational flow structures, which are called as turbulent eddies. So, if you look closely into a turbulent flow, you will find that there are structures which tend to have rotationality, and some of these would be very small, so minuscule that they are very difficult to detect, again some may be extremely large. That means, that they are widely varying in terms of their lengths, also time scales, in the sense that how rapidly are they evolving. The shear and normal stresses that we learnt earlier are now augmented. So, the shear and normal stresses that we defined earlier in the form of taus and sigmas were by assuming that the flow has a laminar behavior. But when we account for turbulence, some additional stresses come into the consideration, which are purely by virtue of these fluctuating components. So, turbulent fluctuations are the root cause behind some additional stresses which are felt in the field. These stresses are called as the Reynolds stresses. There is a little bit more that we need to look at. So, fluid volumes which are initially separated by a long distance can be brought close together by the turbulent eddy motion. That is, by virtue of these fluctuations, distant volumes can start interacting with each other. As a result, heat, mass and momentum transfer effectively exchange in this situation. So, the turbulent eddy motion bring in effective exchange of heat, mass and momentum, and we are essentially talking about effective mixing of heat, mass and momentum through these fluctuations, and they give rise to high values of diffusion coefficients. So, it is not only molecular diffusion that is happening, there is augmented diffusion because of the turbulent eddying motion. When a turbulent boundary layer is formed on a surface like a flat plate, eddies whose length scales are comparable with that of the flow boundary in the sense the characteristic length scale of the problem, the length of the flat plate, as well as eddies of intermediate and small size exist in the flow. So, we were talking about a range of length scales of these eddies. Some of them are very large, typically which can scale with the dimensions of the boundary over which the boundary layer is existing, or they could be very, very small, many orders smaller than the boundary dimension. The largest turbulent eddies interact with and extract energy from the mean flow by a process which is called as vortex stretching. So, there must be some energy transfer in order to keep the turbulence sustained, and that energy essentially is extracted from the mean flow by the largest turbulent eddies. So, this is how turbulence sustains itself. If there are conditions in the flow field where this does not assist the turbulent flow, then the turbulence in the flow can decay. On the other hand, if there is enough energy coming in from the mean flow, then turbulence would sustain and could also get augmented. We were discussing about Reynolds decomposition. Now, when we use Reynolds decomposition and we apply it to the Navier-Stokes equation, what we get is Reynolds averaged Navier-Stokes equations. In the literature, you will often find it mentioned as runs. And if you look at these equations, you will find that the normal and shear stresses that we learnt about earlier, where as I said that we accounted for only the stresses which will occur in a typically laminar flow field. Here you will find that they are augmented. We are continuing the discussion in the context of an incompressible flow. So, thereby you will notice that we have dropped out a term like this, divergence of velocity with a lambda, because divergence V goes to 0 for incompressible flow. So, that has not been considered. You are only considering the 2 mu del u del x, but here there is an overbar because this is coming from the mean u velocity, the time mean of the u velocity. And then comes an additional term which we did not see earlier. This is the additional stress which comes due to fluctuations. You can see that it is dependent on the u dash, the fluctuations along the x direction in the u component of velocity. Similarly, if you go to tau x y, we have written it earlier in this form. Only thing is that in the earlier case we did not have an overbar because there was no separate mean and fluctuating component. It was only the mean itself, and this is the additional stress that is coming. In tau x z, you get a del u over bar del z, del w over bar this should be a y, this should be a x, sorry, there is a mistake here. Okay, and then you get a. So, these are the additional terms in the stress equations, and this is what is called as Reynolds stress. So, if you put these stresses together in the form of a matrix, we call that as a so called Reynolds stress tensor. It has a 3 by 3 structure. That matrix has a 3 by 3 structure. You can try to explore that on your own. We were discussing earlier that when we compare a laminar boundary layer with a turbulent one, we find that the turbulent one is having higher velocities closer to the wall. That is what we mean by the expression fuller. And that is what we meant by saying that there is augmented diffusion of momentum. This increase in velocity closer to the wall or the boundary is happening because more momentum from the outer flow makes its way closer to the wall. What is the consequence of this? The consequence is that this turbulent boundary layer will have two features. One is that the stresses within it will be higher. Why? Because the moment the gradient del u del y becomes larger, automatically it will mean that the tau will increase, which means there will be higher skin friction, which will be produced by a turbulent boundary layer. But additionally, this turbulent boundary layer is more robust in the sense that it can withstand higher adverse pressure gradient, and that is a very, very favorable property, because if it can, then it can delay flow separation. So, you may recall that the leeward surface of the airfoil was drawn like this, and we discussed about flow separation in that context. So, the same leeward surface when exposed to a laminar boundary layer may see a flow separation at a point like this, say x laminar, and see a flow separation somewhere here, which is x turbulent. Why is it? Because this is the laminar boundary layer and this is the turbulent boundary layer, and you see the turbulent boundary layer has much more momentum closer to the wall, and that is what keeps it going against the adverse pressure gradient and delay the flow separation. What is the consequence of this? If you look at, say, a bluff object like this, we know that these objects have a much wider wake. But if flow separation can be delayed, then perhaps the wake width will reduce. What will that cause? Decrease in drag, but more specifically, this is decrease in pressure drag. What do we mean by that? We mean this, that why is drag occurring over here? It's occurring due to two sources. One is pressure drag, another is skin friction drag. The pressure drag is occurring because of an imbalance in pressure between the front half of the cylinder and the rear half of the cylinder. So, let us say this is the stagnation streamline, which we were discussing about in the context of pitot-static tube. So, this is coming and meeting the cylinder at the front stagnation point, let us say O, and then you move clockwise by an angle of 90 degrees and you reach a point A, and anti-clockwise by 90 degrees to reach a point B. So, you can understand that this line AB will divide the cylinder into two halves, the front half and the rear half. Now, if the pressure on the front half is exactly equal to the pressure in the rear half, then the pressure drag, let us say dP, will be 0, because there is no imbalance in pressure between the front and the rear, and therefore, along the flow direction that will end up producing no drag. Remember that here the angle of attack essentially is 0 and the drag is basically the axial force, the lift is basically equal to the normal force. Now, because the body is symmetrical about the horizontal axis, the flow does not turn in any particular direction and therefore, there is 0 lift. But the drag could be there if you have wake formation. What happens is that the pressure in the rear half is on an average lower than that of the front half, and there is a non-zero pressure drag in that case. And when does it happen? It happens for viscous flow, because the flow can separate. So, in a bluff body, if you can delay the separation, you can reduce the pressure drag, and in bluff geometries, the pressure drag is the dominant part of the total drag. So, the total drag is the sum of these two in general. There are some other sources of drag which are not applicable here. So, if pressure drag is important for bluff bodies, you can reduce that and thereby reduce the total drag significantly if the flow is turbulent. On the contrary, if it was a streamlined body like an airfoil, this airfoil will have a very thin wake, especially at low angles of attack. Thus, pressure drag is not the dominant drag. The dominant drag is the skin friction drag, and that can be reduced if the tau on the surface of the airfoil can be reduced, and that can happen if the del u del y is smaller on the wall, and that happens if you can maintain a laminar flow. Therefore, laminar flow is more suitable for flow past an airfoil, especially at low angles of attack, and turbulent flow is more suitable for a bluff body to reduce its pressure drag. These are general rules, but they give us a lot of understanding about the flow physics. We need to remember that there are certain factors which can augment turbulence. If the surface roughness is high, then turbulence is created earlier, that means the critical Reynolds number reduces. It can be also caused by certain ambient disturbances in the form of acoustic disturbances, vibrations, etc. If you heat up the wall over which the boundary layer is formed, it will augment turbulence. You can also trip the flow by putting some small obstacles on the surface, and turbulence will happen immediately. So, these are things which can augment turbulence. Additionally, adverse pressure gradient triggers turbulence earlier. So, we briefly discussed about different aspects of laminar and turbulent flow. So, in this lecture we completed our discussion on boundary layer flows with a section on the displacement thickness. Subsequently, we briefly discussed about basic concepts of laminar and turbulent flow, mainly in the context of boundary layer. Thank you.